Hi, today I'll be going over Rosetta Antibody Design. Rosetta Antibody Design is a generalized framework for the design of antibodies, in which a user can easily tailor the run to their project needs. The algorithm is meant to sample the diverse sequence, structure, and binding space of an antibody-antigen complex. An app is available, and all components can be used within RosettaScripts for easy scripting of antibody design and incorporation into other Rosetta protocols. I'm not going to go and read all the background text of this tutorial. You're free to do that as you wish. But I will go through this tutorial step by step and run all the commands within to make sure that you know exactly what you need to do to produce the correct results in this tutorial. First, we'll be going over the general setup and inputs. First is the Antibody Design Database. This app requires the Rosetta Antibody Design Database. The database of antibodies from the original North clustering paper is included in Rosetta and is used as a default in this tutorial. An updated database can be downloaded by following this link. Next is the starting structure. This protocol begins with the three-dimensional structure of an antibody-antigen complex. While any antibody-antigen complex can be used, it is recommended to use a native and experimentally determined structure to improve the final result. 3. Model numbering and light chain identification. The input PDB file must be renumbered to the AHO scheme and the light chain must be identified. This can be performed using the PYIG classify server from this link right here. For this tutorial, the starting antibody is already renumbered for you. 4. Notes for tutorial shortening. While doing actual runs of these tutorials or to use your own system, you'll need to generate thousands, maybe tens of thousands of structures. However, in the interest of time, we will run these tutorials in a very shortened manner, producing very few structures. We'll set outer cycle rounds to 5 in order to run these quickly. Finally, general notes. This tutorial assumes that you have Rosetta already added to your path variable, as this is how Rosetta is generally run. If you do not have this done, add the Rosetta application to your path. For example, if you're using TCSH shell, you can follow these two commands here. Also, we'll be using the JSON output of the score file, which is much easier to work with in Python and Pandas, and when generating a large amount of data. This will be done by using the option score file format JSON. Finally, all tutorials have generated output in the output files and their approximate time to finish on a single Core i7 processor. Now let's look at Tutorial A, General Design. Just a note, in many of these examples, we will use the application for simplicity. However, all options are available using the Antibody Design Mover, so you can use XML if you're interested. So let's copy over the files we need first. Now we're in the Antibody Design directory right now, and if we ls, we can see the files in here. We have input files and output files, which you can use throughout the tutorial in case you need them. So let's copy the files we need first. First, we're going to make a directory, then change directory, and now start copying over from the input files. These files we'll use throughout this first tutorial, and now we can see them all there in the directory. Now we're going to start design on a new antibody that is not bound to the antigen in the model. Therefore, this is not a crystallized or a co-crystal structure. These are two different PDBs put close together that we're going to try to design. Therefore, it's unlikely that this will actually work in real life. We're starting off with an antibody that expresses well and is thermodynamically stable, and has been shown that it can tolerate multiple CDRs of different sequence and structure. Therefore, it is a good template for design. Then the protein that we're using is 1QAW. It's an oligomer of the TRIP RNA binding attenuation protein. It's a large ring-like structure, which you'll see in a moment. And what we're going to do is design an antibody that binds to a dimer of the attenuation protein. So let's open this up in PyMol. That'll just take 1 second. And we'll color by chain, just nice and easy. And so we can see the antibody right here and place close to a dimer of this attenuation protein. So it's these CDRs that we'll be designing throughout this tutorial. So let's go ahead and close that. And now that we've set up this, we'll move on to the first tutorial, sequence design. Now let's look at sequence design. Using the application is as simple as setting the Seq Design CDRs option. In this tutorial, we're just going to do sequence design. We're not going to swap out any CDR loops. We're just going to design the CDRs that we set in the command line using this flag and letting us design L1 and L3 CDRs. Remember, we have to let the program know which light chain we're using. We're going to set the nstruct to 5, so we only produce 5 output models, so this will run very quickly, and set the prefix that all the output files will have the name start as. So let's run this. So it's antibody design. The input file is myab.pdb. Seq design CDRs L1, L3. Set the light chain to kappa. The nstruct to 5. And the out prefix to tutorial A1. And then we'll run it. Now this will take about 227 seconds to run, so I will not sit here and show you the entire output, but as you can see here, the program is starting to run. So we'll let this run and come back in a few minutes. All right, the program is finished running. We can see that it took 215 seconds, so definitely not too long. And we can see if we ls the output, we can see 1, 2, 3, 4, 5 output structures named tut.a1 myab underscore 0001.pdb and so on through 005. We can also see the output score file for this command. Next, we're just going to run interface analyzer to score the input pose. We're just scoring the native structure to get a reference energy to compare our structures to. So we'll use interface analyzer, use the input file myab. Now we have to define the interface, the light chain and the heavy chain, L and H, and then the rest of the chain from the opposing protein. And then we're just going to set our output prefix to native and run that. And as you can see, that ran really quickly. If we just ls that, now we can see that the native score file exists as well, and we can use this as a reference file to compare all the designs that we've made. Now that we have our native structure scored, let's take a look at the score file and analyze it versus the native. So we'll use the scorefile.py program. Now we're looking at the DG separated score, so that's the difference between the packed and unpacked. Alright, and now we can see our sorted scores. So these output files are, you can read them, but they're a little hard to read, so just using the scorefile.py, this is the easier way to analyze your results. So we can see here that all of our scores range from 1,780 to 2,877. Now in Rosetta, the lower the score, the better, so this is our top model right now. Of course, usually in Rosetta, especially for these delta G of separated scores, we'll definitely want to have negative scores. So right now, these energies are very, very high. But we did very limited design, so it's very hard to tell. So it's obviously difficult to assess how well we've done. And also, we've only generated 5 models. If you were doing this for real, you'd be talking about generating a couple thousand models. So let's just check to see how well it scores versus the native. So we can run a similar command to that, but now just looking at the native score instead. Alright, and we can see that the native score is over 12,000 compared to 2,000. So definitely an improvement. Of course, these energies show that these structures are unlikely to bind to one another in an experimental setting. Alright, now we're moving on to tutorial 2, Graft design. Now we'll be doing graph design, that is swapping in and out the CDR loops, and sequence design on loops L1 and L3. With an end struct at 5, this means we'll be generating 25 design trials total. So this is the command we'll use, very similar to before. We're going to use, once again, the input file myab.pdb. Now we're using the graph design CDR flag, L1 and L3, the seq design flag, L1 and L3 again, setting the light chain to kappa, the end struct at 5, and for this, the out prefix is set to tutorial A2 underscore. And we'll let this run again. Now, it will take about 740 seconds total, so I'm not going to show this whole thing, but as you can see, it's running and not erroring out so far. And if you were to do this via the RosettaScripts or XML, this is the command that you would use. Alright, now this tutorial has finished running. As you can see, it took about 715 seconds to run, so significantly longer than the first one. Let's ls this output, and as we can see here, now we have tut A20001 through tut A20005. And once again, we have the output file right here. Now, typically we're going to require a much higher outer cycle rounds number than we use here to generate enough stochastic models to find a good low energy solution. So let's see, by running the summary command from tut A1 and tut A2, if we've improved at all. So let's run that command. And as we can see here, we've generated 5 models for each. This is TUT A1 up here and TUT A2 down here. And as you can see, the min has decreased, the max model score has decreased, and overall the mean has dropped by about 100 Rosetta energy units between the two. So as we can see, definite improvement. Now we can also look at the scores of the native TUT A1 and TUT A2 and look to see what the results look like there. So scores, DG separated, output tab, and then native score.sc, TUT A1, score.sc, TUT A2, score.sc, and then we'll sort our results. All right, and as we see here, we have the native, around 12,000 Rosetta energy units, and 3 of the TUT A2 structures are lower energy than any one of the TUT A1 structures. So by swapping in and out the CDR loops, we can see that we have had some minor improvement in the results. This may or may not happen for you because, like I said, we're only running 5 models, which is very low. Additionally, then, we can look to see what the models look like. So if we open them in Pymol, we open up our native structure, and then all the TUT A2 structures. Just give that a second to load. All right, so we can see our protein that our antibody has bound to, and we can see all the different models, one on top of one another, and then run the command color cdrs.pml, and this will color the loops, the CDR loops different colors. So it's a real nice way to just look at your structures. So we'll be looking at the L1 and L3 loops to see if they've changed in length. So if we just pull it up closer here, we can begin to look at the loops. Now I'll let you analyze this yourself. I don't want to give you all the answers. But as we can see here, this is a great way to be able to analyze your output structures by actually opening up in Pymol and seeing what they look like. Now we'll be doing a basic de novo run. Here we're just doing a de novo run without any docking, starting with randomly grafted CDRs. This is instead of the native CDRs that we've used in the last one. This is just the CDRs that are in the PDB to begin with. By swapping out to randomly grafted CDRs, this starts us as a higher energy, so we're more likely not to be trapped in a local energy minima. So let's run this command now. Very similar to before. Once again, the same input structure, graph design, CDRs, L1 and L3. We're running sequence design again. Setting our light chain to kappa. Well, not setting, but declaring that our light chain is kappa. And now adding the flag random start. So this will give us a random starting CDRs for L1 and L3. And our out prefix is going to be TUT A3 underscore. And we're going to run this one. And once again, here's the XML command if you want to run via RosettaScripts. So because we're only doing an nstruct of 1, this will only take about 2 minutes, so not as long as previous ones. We're not really going to go into the results of this because we're only generating one structure, so it won't really tell us much. But it's always nice to know that this flag exists, this random start, just to make sure you know how to do it and helps you escape from any local energy minima. Now we're going to look at tutorial 4, RosettaScripts RAbD framework components. So this will give us an introduction onto using designing your own XML to add flexibility into the RAbD framework. So it's really flexible that you could then combine with other components of Rosetta that you're interested in. So it's a really great way to add flexibility. So first we're going to copy over the files from the input file directories. Remember, for all of these tutorials, almost everything you need is within these input file directories. So we'll copy over the XML, and we'll copy over the PDB file that we'll be using. So first we're going to take a look at the XML. This is always good to do before you start anything, is look over the XML and see what it actually does. So we've opened up the XML here, and what I always like to do is start from the bottom and work up while looking at an XML. Because down at the bottom is where you actually have your protocol section, and this is what actually is going to be run in your XML. If something isn't explicitly placed in the protocol section, even if it's defined up above, it won't run. So as we can see here, the first protocol we do is run these metrics on the native antibody, so just get some statistics on the native antibody before we start. Then we graft light chain CDRs from our donor onto the antibody that we're using. Then we're adding constraints right here. Then designing the actual framework by alternating cycles of packing and minimization. And then we'll just use a simple metrics protocol to analyze the results. And so we can see up here, I'm not going to go through line by line, but we can see here in the movers section, we've defined all these movers that we're going to then run down in the protocol section. You can see where we're defining dihedral constraints. You can see where we're defining our antibody CDR grafter, which CDRs we're using, our pack rotamer movers, where we're just restricting to packing via the CDRs, the minimization mover, and then the simple metrics that we're defining. And we can see all these residue or all these metrics that we're doing. And the simple metrics then are defined up above here, and we can see the name of the simple metrics. These are sequence metrics, for instance, the residues that we're selecting them on, for instance, which are defined once again up above here. So, like I said, always a good idea to go through your XML, read from the bottom up to see what you're going to be doing. So now let's close the XML, and just to let you know, you can follow a lot of these links right here to see information on RosettaScripts, on antibody and CDR specific operations in RosettaScripts, and the modeling and design movers of RosettaScripts with specifying antibodies. So next, we'll move on to actually running the protocol. So let's run it right here. So it's going to be a slightly different command to begin with since we're using RosettaScripts, so we'll have to use that instead. So RosettaScripts, Linux GCC release, and we start off with parser protocol, and this is where we'll define the actual XML. So AB design components.xml, defining our input, antibody scheme, AHO numbering. CDR definition is going to be the North definition from the North et al. Paper that we discussed about in the intro talk to these tutorials. The input structure is once again the myAB. Out prefix is tutorial A4 underscore. Nstruct is going to be once again 5 residues. Score weights is going to be ref 2015 and the Cartesian minimization version of the ref 2015. And we'll set this check CDR chain breaks to false. And we'll run that. And this will take about 400 seconds, maybe a little less. once again, not going to sit through and watch all of this, but as you can see, it started running correctly, and so we'll let this run. Alright, that's finished running. Now you can see that this has taken about 440 seconds, so a little longer than what was shown in the tutorial, and that'll sometimes happen. So now let's look at our output, and we can see we have tutorial A4, MyAB0001 through 0005. And once again, we have the score file. So now we want to look at the score file, look to see if the sequences are different than what we started with, and the interaction energies. So we can look at the score file here. And obviously, this is in a database format, so really hard to read. But you can see that, for instance, we have the design L1, L2, and L3 sequence here. And we can also see the native sequence L1, L2, and L3. So it's a way to compare the two. So you can obviously fish this out individually. But if you're just looking at everything at once, this is the way to do it. So yeah, just use the score file command as previous and look at this one instead to look at the differences between everything. Next, we are going to move on to tutorial B, optimizing interface energy. Let's start with section 1, optimizing DG. Here we're going to set the protocol to optimize the interface energy instead of the total energy. So the total energy is the entire energy of the system. That is the energy of the whole protein and of the whole antibody, regardless of not if it's at the interface. Here we're just looking at optimizing interface energy, which essentially in this case means the energy of the bound versus unbound state. So we're going to add this flag to our protocol, this -mc optimize DG. So we're going to optimize the delta G of the system. So we're going to run the command similar to before. We're going to use the same input file, the myab.pdb, Graft design, CDRs, once again L1 and L3. We're going to do sequence design on L1 and L3 as well. Define the light chain as kappa. And this is where we're going to add our MC optimize DG flag. Same as before, set our end struct to 5. And in this case, we're going to set the output prefix to tutorial B1. And then let this run. Now, this takes a lot longer than some of the previous tutorials, about 800 seconds. So I'm going to see you once this finishes running. Okay, the tutorial has completed. As you can see, it took about 1,000 seconds total. So kind of long, but it hopefully is worth it. So now let's compare this to tutorial A2 to see if the interface scores have improved at all. So we can use the score file command. Once again, we're going to look at the DG separated scores. We'll include the native score as a control, tutorial A2, score.sc, and then tutorial B1, score.sc. Alright, so we can see the native, once again, about 12,000 Rosetta energy units. The tutorial A2, our low score is 1,600. And as you can see here, This 0005 model is about 1300. And overall, you can see that most of the scores are lower than the tutorial A2. We have this model here that's higher at about almost 5,000 Rosetta energy units, and that'll happen due to the stochastic nature of Rosetta. Next, we're going to optimize the interface energy and the total score, or energy. So here we want to set the protocol to optimize both the interface energy and add in some total energy to the weight. So because the overall magnitude of the total energy is going to be a much larger number than the interface energy, we're only going to include a small percentage point of total weight, of the total weight to this total energy, so 0.01 to 0.99. Including total energy, make sure you remove some structures that while the interface energy may be really optimized, you've done something to the one or the other protein that really messes up the overall shape or energy of the total structure. That'd mean this protein is unlikely to fold into this orientation. Another way of doing this is to optimize for the interface energy and then just sort out some of the really high scoring models as well. But this is another way to do it, and might be a good idea to do this if you're having very bad total energy while you're optimizing the delta G. So really just another option in this protocol that you can consider using depending on what's happening with your output. So let's try running this. So the command is going to be, once again, very similar. My antibody again .pdb, Graft design, CDRs, L1 and L3 again, seq design, CDRs, L1, L3, light chain is denoted as kappa. Once again, as the previous tutorial, we're going to use the MC optimize DG, set that flag, MC total weight. So this is what we're doing differently in this tutorial, setting this total weight to 0.01 of the total weight that we're optimizing. Then the MC interface weight to 0.99. So this term will dominate, but it also will be a smaller magnitude than the total energy. And struct at 5, and the out prefix to tutorial B2 underscore, and then let's run that. And once again, this will take about 900 seconds, so I'll let this run and I will see you on the other side. Okay, the tutorial is finished running. Took about 930 seconds, so once again a little long. If you want to skip this and just use the files in the output directory, you can definitely do that as well. So now we're going to use the scorefile.py script to compare the total energies of this run versus the B1 tutorial to see if this has improved our total scores. So instead of the DG separated energy, we're going to use total score because that's what we're interested in. We'll just include the native again just to see. So tutorial B1 and tutorial B2. Oh, and we can sort this as well. The native actually doesn't have a score because just remember we didn't actually run it through there, so this will be 0, but that's fine. As we can see here, tutorial B1 actually wound up with a lower total score than B2, and this will happen because we've only generated 5 total output models, so stochastically this will happen. If we ran more, we'd probably definitely see an improvement in the total score of the B2 versus B1. So definitely something to keep in mind, that sometimes when you have just so few models, you really don't see the intended effect of some of these flags. Let's move on to tutorial part C, towards de novo design, integrated docking, and design. So this is where we really get into something that you would actually use on a protein, well, really an antibody of interest. This is where we're doing not just design, which is what we did in tutorials, the sections A and B, but actually including docking into the process. This allows flexibility of where the interface of the antibody and protein actually occur. You'll constrain that definitely to keep the epitope and paratope near one another, but without some docking in the system, we won't really be able to really optimize the interface like we can with this protocol. So just to note, this tutorial takes a very, very long time to run, over 1,000 seconds for an nstruct of 1, and in the case of docking, we really need to generate hundreds or thousands of structures to really get a good picture of the energy landscape that we're designing in, because we've now added a really multiple degrees of freedom to this system. So what we're going to do in this case is not run the actual tutorial, although the command is given right here, but we're going to use pre-generated output. This way we can analyze what a larger run really looks like without having to do all the work ourselves. Another thing to note is that for this tutorial, for this example, we're using MyAB relax. So previously, we'd just been using the myab.pdb. So here we're going to have to copy over from the input files myab relaxed. This is just a relaxed version of we put it through the Rosetta Relax protocol, and it'll just keep us from really designing optimizing a non-optimized structure. This will just get us more reliable Rosetta energies than the just standard crystal structure of MyAB. If you're curious, you can run both and see the difference, but I'd advise you to just use the relaxed structure. So here's a command. Like I said, I'm not going to run it, but it's the same start, AntibodyDesigner.Linux GCC release. Now we're using the myab relax.pdb as the input structure. Graft design CDRs. In this case, we're doing L1, L2, L3, H1, and H2. So we're grafting all of the loops except H3. And then sequence design on all 6 CDRs. Once again, setting that kappa is the light chain. We're going to optimize the delta G. And this flag is our different one, is the do dock. So we're actually going to do docking in this case instead of just the static design that we were doing before. So in the static design, we weren't moving the antibody in respect to the protein at all. The side chains can move, the backbone can move, but the entire two-body system could not. We're setting the nstruct to 1,000 in this case, instead of just a 5 before, because otherwise we won't really have a good profile of the energy landscape, and setting random start. And then for this, the output prefix is tutorial C1. So, like I said, in this case we would usually run it, but for this tutorial we're going to skip it because it just takes a while. So instead we're going to copy over the files. Okay, so let's pretend that that's finished running. Like I said, it's going to run a very long time, and with 1,000, this is definitely something that you'd want to run on a cluster. So let's pretend that's finished, and now copy over the files instead from the provided output directory. So copy output files and then top 10 C1, copy it to this directory here. Also copy over the score file, .c1 score.sc. And now let's look at this in PyMol. Load the original file, we'll do the relax in this case, and then the top 10 structures as well. We'll just use the wildcard there to include all of them. And then also while we're in PyMol, if you want to use the provided labeling scheme, we can use this @color_cdrs.pml. And this will color then the different CDR regions to the provided color scheme. So in PyMol, if we just look at the original structure, this MyAB relaxed, we can see where the original antibody, where we were trying to design this region of the protein. And now when we look at the top 10 structures, we can see that they've drifted all to the middle and bound at this region in kind of the center of the protein complex. So this will happen. We do have paratope site constraints to constrain it to the paratope. And if you can see here, let's take this top generated structure. We can see that the CDRs are what's binding to the protein of interest. However, not in the region that we were designing to. But we don't have any constraints set to the epitope region, or at least the epitope region of interest that we have. So yes, in all cases, we've moved from where we thought we were designing to this, what Rosetta found, a better region to design to. But we definitely don't always want this. So this is something that we had to look at. We have to include constraints to keep it in the region that we actually want to design. So you can look through this more, but this is just kind of walking you through what you might see in the output. So see in the next part of the tutorial where we'll talk about trying to constrain this a bit. Okay, let's move on to part 2 of tutorial C. So in the last tutorial, we found that the antibody really moved from the starting position that we had manually docked it into. So here we will again perform docking and design, but we will be incorporating auto-generated site constraints to keep the antibody somewhat locked around the starting interface residues. So this is essentially automatic. These residues are determined by being within 6 angstroms of the CDR residues by using this use epitope constraint flag. So this is fairly automatic on your part, so you just really need to use this flag. Obviously, you can customize this a bit more, but this is a good way to start. So once again, this is going to take very long to run, so I'll explain the command, but we won't actually run it. So antibody designer, Linux GCC release, use the relaxed antibody as the input structure, Graft design CDRs L1 and L3. So we're doing a little more limited design in this case, or limited grafting in this case. Sequence design, we're going to design all 6 CDRs, assign the light chain as kappa, optimize delta G, we're going to do docking again, and here's the real difference, use epitope constraints. So we're just constraining that input from where the antibody is assigned in the initial PDB, in this MyAB relax PDB. Set the nstruct to 1000 so we properly explore the energy landscape, and then the out prefix of tutorial C2. So let's pretend to run that, but once again we'll just get that from the output files directory. Okay, let's pretend that's finished running. Now we'll just copy over the files from the output directory. So cp -r, and then the output files directory, the top 10 from tutorial C2, copy them to this directory here, and also make sure to get the score file as well. All right, so now they're in this directory, so we'll load these up in PyMol. Top 10 C2 and use the wildcard, so we load all 10. And once again, we'll load the native structure in as well, just for comparison. And great, you can see that now we have the original antibody structure, and then all 10 of the newly docked antibody models are basically within the same position as before. So we can once again load in the PML script to color these nicely and to highlight the different CDRs. But the main thing is to note that the flag use epitope constraints actually worked, and it kept everything around that design position. It's a great way of just keeping things locked in place, or relatively locked in place. You can definitely see some motion, more motion than you did in just the design tutorials earlier in parts A and B. But it keeps it from moving to other parts of the protein complex entirely. So this is great. Okay, let's move on to part 3 of tutorial C, specific residue epitope constraints. So very similar to part 2, performing docking and design with epitope and paratope restraints, but in this case we're going to be a little more focused. So in this tutorial, what we're going to do is use epitope constraints and define the paratope that we're interested in and specific residues in the epitope that we're interested in as well. So once again, this takes a while. This is something, especially with an nstruct of 1000, that we're looking more of running this on a cluster than your individual laptop. So I'll walk through what the command is, but we're not actually going to run it. So AntibodyDesigner.Linux GCC release. Use the myab relaxed as your input PDB, Graft design CDRs, as in tutorial 2, L1 and L3. The sequence design CDR flag, we're going to list L1, L2, L3, H1, H2, and H3, so all 6 CDR loops. Define our light chain as kappa. We're going to do docking, as we've done in the previous 2 tutorials. Use epitope constraints, that's the same as the last one. But this time we're going to define the paratope as L1 and L3, so excluding the other 4 CDR loops, and then define specific positions as the epitope positions on the protein. So in this case, residue 38 on chain J, 52 on chain J, 34 on chain K, and 37 on chain K. Note that these are chain designations and not residue type designations, even though there is no amino acid J. Nstruct 1000, and the output prefix in this case is tutorial C3. So let's pretend to run this. Alright, so let's pretend that's finished running. And now we're going to actually copy over the files from the provided output files directory. So cp -r, and then output files, top 10, now from C3, copy it here. And then once again, make sure to copy over the correct score file as well. And now we can load that up in PyMol. And yeah, use the wildcard character to make sure you grab all 10 and load that up. And now in this case, we're not going to see, at least in this kind of wide view, much difference between tutorial 2 and tutorial 3. In this case, we're going to more look into the specific residue contacts that occur and the overall energies, both in delta G and total energy. And in this case, sometimes you're not even going to see much improvement, but you're going to define these specific residues because some experimental evidence has been found to show that these residues are important, be it sensitive to mutation or something like that. So that's really why we would do something like this. Or if your antibody is really drifting and you want to make sure to maintain some contact that computationally you found has been important. So we can once again load color cdr.pml script, which will nicely color all the loops, and then I'll let you analyze this yourself. Additionally, what you can do is use the provided scripts to analyze the total energy and the delta G energy, and really start to kind of look on a model-by-model basis which models are the best if using all of these defined paratopes and epitopes really help define your model. Sometimes, without a large number of structures generated, you're not going to see a big difference, but it's definitely something to look at, and especially in your use case. All right, let's now move on to tutorial D. So advanced settings and CDR instruction file customization. So in this part of the tutorial, we're really going to get down to the nitty-gritty parts of RAbD. So in part 1, we're looking at the CDR instruction file. This is really just allowing you to really customize the protocol that you're using for the design run. So an instruction file is provided, and in this case, what we're going to do in this my instruction file is specify the lengths of the CDRs that are included to create a larger interface area. There's also a default CDR instruction file for you to look at as well. So let's copy both of these over from the input files directory, my instruction file, and then in the input file is the default CDR instructions. And so we can just use a text editor to look at this. And so in this case, we're setting the minimum length for H1 to 13 residues, for L1 setting the minimum length to 12, and for H2 setting the minimum length to 11. So in this case, like I said, just to try to create a larger interface area. And you can also look at the default CDR instructions as well. These are loaded by default, but it's definitely something to look at. And then you can also customize these further. So this is now the command to run this. Very similar to the commands we've run before, as usual. So in a lot of cases, it is just small variations on the larger theme, but you can just see the amount of customization that you can do with just a few flags here and there. So in this case, we're grafting L1, H2, and H1 for the sequence design. L1, L3, H1, H2, and H3. Define the light chain as kappa. The CDR instructions, so this is new for this tutorial. And then the my instructions, and like I said, those are just specifying the minimum lengths. Random start, nstruct of 5. And then in this case, the out prefix is going to be tutorial D1. And let's run that. And this will take around 800 seconds, so I will see you at the end of this design run. Alright, so that tutorial is finished running. Took about 700 seconds. So we're not going to analyze the output all that much. We can see now we have tutorial D10001 through 005, as well as the score.sc file. So in this case, we can look at the output real quick. Load in the MyAB just as a control, and tutorial D1, and then wildcard.pdb, so we load in all 5. And then we're going to just load up the color cdrs.pml. So in this case, what we've done with these instructions is set the length, the minimum length for L1, for instance. So we can just look here, look at the L1, we can see the native up on top, and we can see that for each one, the L1 CDR length is 12 or more in each case. So the instructions have worked as intended. Alright, now let's move on to part 2 of section D, disallowing amino acids and controlling design via the Resfile. So in this tutorial, we're going to disallow any sequence design into proline and or cysteine residues, and then also doing further limiting using Resfile to limit design at specific positions. So we're going to do 2 slightly different things here, but the same general effect. So first off, we're going to copy over the Resfile. So this is once again in the input file directory, and my resfile.resfile, and copy it the current location. Let's open up my Resfile and just analyze it really quick. We can see here we have 4 lines. The full information for Resfiles are at this hyperlink right here, but we can walk through these 4 lines real quick. We just have the start line, and then position 134 of chain H. We're just going to have just the native amino acid at this position. Position 40 on chain H, only the native is allowed here. And then at position 28 on chain L, just the pick from these residues, and that's a tyrosine right there. You can list as many residues as you want. So just 3 on this line. So that's what we're doing in the Resfile in order to limit the design. And remember, this is just to limit the design residues. We're not turning on any residues in the Resfile. That's not what the Resfile is used for. So let's run this command, antibody designer. Use the MyAB as the input file again. Seek design. CDRs, L1, L3, H1, H2, and H3. State that the light chain is kappa. And this is where we're including our Resfile with the Resfile flag, my resfile.resfile. So that's we're including those 3 residue limiting positions in the Resfile. And then here we're just kind of doing things globally. Disallow amino acid, proline, and cysteine. Set the nstruct flag to 5, so only 5 models that we'll be generating in total, and set the out prefix to tutorial D2, and then let's run this. And this should take about 200 seconds total, so I will see you at the end when this completes running. Alright, that tutorial has finished running. It took about 235 seconds. And as you can see now, we have the output tutorial D20001 through 005, as well as the tutorial D2 score file. I'll let you look at it to see if Rosetta has respected your Resfile and the disallow AA. Considering we generated so few structures, you might not see a difference between the D1 versus D2 tutorial, just because with only 5, the likelihood of designing into proline or cysteine is somewhat low. But definitely take a look at it and see if your results have changed. Okay, let's move on to part 3 of tutorial D, the minimization type. So here we're changing the minimization type to relax. Obviously there's a lot of technical things going on in the background, but the main thing that this minimization type enables is flexible backbone design. So you're going to see more flexibility within the backbone. So the default is to use the min-pack cycles, but relax overall works better. But as in most cases, there is a trade-off, and in this case, the trade-off is time. So in this case, it takes about 350 seconds for just one model to be generated. So definitely something that we're not going to design a bunch of models on, but it's something that you would definitely want to consider using for your designs of interest. But once again, definitely consider running this on a cluster or somewhere that you can definitely take a lot more time. So let's look at the command. Antibody designer, Linux release, the myab.pdb file for input, seek design, CDRs, L1, L3, H1, and H3. Define our light chain as kappa. Once again, we're just going to define the Resfile. Not necessarily that you would need to do this using this minimization type, but we're just going to keep doing what we've done in the previous section. Disallow the amino acids proline and cysteine. Set the min type to relax. Instruct, like I said, we'll just do one in this case because it takes a while compared to our previous default, and set the prefix to tutorial D3 underscore, and let's run this. And like I said, this will take a bit, so I will see you at the end of the tutorial. Okay, so that's finished running, and like I said to begin with, it takes about 315 seconds for one instruct, so definitely increases the time that this takes to run. So if we want to analyze the output, we use the score file command again, look at the scores, DG separated, and then for output tab, let's look at then the D2 score and the D3 score. And then we can just run that. And okay, as we can see here, the tutorial D3, 172 Rosetta energy units versus the low one for this is 160. So not quite as low, but as you can see, lower than most. And if we'd run this for 5, 10, 1,000, we definitely see a decrease in the total score using this minimization type versus the other one. Let's move on to section 4 of tutorial D, framework design. Now we're getting into things that you can do using this program, but not necessarily that you should do or in typical cases. But it's good to know the flexibility that's involved in this program. So we're going to be allowing the framework residues to design, which isn't necessarily something that you shouldn't do. But what we're going to do is we're going to disable conservative framework design, so pretty much it can be designed into anything that you want and not keeping with traditional, really conservative residues in the framework. In addition, we're also going to be using the flag, the design antigen option, so this will actually design the antigen as well as the antibody. This can be useful for vaccine design. Really, it's unlikely that you would use all three flags at once. But once again, this is just showing what you can do and not necessarily what you always should be doing. So let's take a look at this command. Antibody Designer, Linux GCC release. The input structure is my ab.pdb. Seek design, CDRs L1, L3, H1 and H3, light chain defined as kappa. We're going to include the Resfile. Once again, you don't need to do this to use these other flags, but we're going to keep it from the previous examples. Disallow the amino acids proline and cysteine. Minimization type, relax. So we're using that flag again. Once again, don't need to use that flag when we're designing the antigen, for instance. So this is the design antigen flag, so we're actually going to be designing the antigen in this case. Design framework, set that flag, and then set conservative framework design to false, so we can really allow a lot of flexibility within the framework design. We're going to set the end struct to 1 and out prefix to tutorial D4, and let's run that. In this case, I spelled end struct wrong, which this can happen to you and will happen a lot. So let's run that again. All right, and now we see this is actually running. And this takes a long time to run, around 900 seconds, so I will see you once this finishes running. Alright, that tutorial is finished running. So you can see it's taken about 1,000 seconds for one model, so definitely something that be judicious running this in a tutorial setting. So if we just look at the output, we can see that, all right, we have one model generated, tutorial D4 0001, and the associated score file. If we just want to pull this up in PyMol, pull up the native file and our design file. And so if we look at it, we can look at the interface. And if we pull up the sequence, we can now see that, all right, this is chain J is part of the antigen, not the antibody. And you can see here, position 35, it was serine in the original, the native, and now is a valine. So we can see that, yes, some design has occurred at the antigen as well as the antibody. So that flag did work. I'll let you analyze the rest of the output to see if things have changed. Like I've said before, if we're just generating one output model, sometimes you won't see all the change considering the stochastic nature of Rosetta, but you will definitely see some changes. Let's move on to the final tutorial of the Rosetta Antibody Design tutorial set, part 5 of tutorial D, H3 stem, KT, and sequence variability. So we're introducing 3 new concepts in this tutorial. This is just really increasing the variability of our sequence design. So a lot of ways to kind of tweak and massage the algorithm to just increase the amount of sampling that's going on. So one of the things we're doing is enabling H3 stem design. So previously we have been designing the sequence of the H3 loop, but not changing the overall geometry. So here what we're doing is changing the H3 stem. That's the residues at the base of the H3 loop, flipping from bulge to non-bulge and vice versa. This now can occur with this flag just to increase the variability of H3. If you do this, you might want to run loop modeling to test the designs to make sure that the H3 loop with this new redesign doesn't change its overall conformation too much. It's something, you definitely have to be careful about since there isn't, these kind of standard canonical H3 designs considering the overall variability in H3 loops compared to the other 5 CDR loops. So just definitely something to be aware of. Another thing we're doing is increasing KT. This is essentially part of the Monte Carlo criterion, and not to get into the math, but essentially this just allows for more designs to be accepted rather than rejected, so it just allows us to get into higher energy states than we could before, accept these, so possibly an increase of sampling space that way. And additionally, we're just changing the sequence design profile samples to 5, so just allowing for more sampling in the number of times the profile is sampled each time the packing is done. Once again, just increasing the variability. So just 3 different ways to, massage the algorithm just to increase sampling. So let's try running this and look at the different flags that we will be using in this slightly new command. Input myab.pdb, seek design, CDRs, L1, L2, and H3, Graft design, CDRs, L1 and L2. Make sure to let the algorithm know that the light chain is kappa. Design H3 stem. So this flag is new, so we're allowing bulged versus non-bulged stems for the H3 CDR loop. KT we're setting to 2.0. Well, the inner KT we're setting to 2.0, as well as the outer KT to 2.0. So once again, just kind of increasing the accept to reject ratio. Seek design profile samples to 5, end struct to 5, and the out prefix to tutorial D5. And once again, you don't need to use all of these 3 new flags that or really 4 flags in conjunction with one another. You can use them individually as your needs arise. So let's run this. And this takes about 450 seconds, so I will see you on the other side when this finishes running. Alright, so this tutorial has finished running. 5 jobs, 5 models that were created, took about 640 seconds. So not too bad, and you can see them right here, tutorial D50001 through 0005 with the score output right here. So I'll let you open up these files in PyMol and analyze them and look at the energies associated with it and see what's all changed. With some of this, kind of increasing the amount of sampling done, once again, you might not see this with only 5 files generated, but if you increase this to 100, 1,000, this is where you're really going to start seeing the variation. So it's definitely something to consider when you're using this for your own work. So now we are done with the tutorials. We've finished everything. So below this in the tutorial is a reference manual for antibody design CDR instruction file. So a lot of information for you to look through, to analyze, and really help you on your journey to really looking through this algorithm. So thank you very much for getting through this entire tutorial, and I wish you the best of luck in antibody design. Thank you.